Alright, we said there's 4 methods for calculating enthalpy or change in enthalpy. We're going to look at the first one in this video, and that's calculate it using average bond and enthalpies. Right, here's a graphic we've seen before. So when atoms are separated, the nucleus of one is going to attract the electrons of the other, and that creates a high potential energy system. Once they pull together and kind of balance out their attraction with the repulsion of the protons, we get a low potential energy system. Now, if we're going from high energy to low energy, that means you're losing energy from this point to that point. Energy cannot be created or destroyed, so where did that energy go? Well, it had to be given off. And it's given off in the form of heat. And so this process then, since it's losing heat energy, would be an exothermic process. So that means energy is released, and it's always released during the formation of a bond. And that's because you have high potential energy, low potential energy, so that energy is lost in the form of heat. So energy formation would have a negative delta H value. It's an exothermic process. And if we think about it backwards, if we break bonds, we're going from low potential energy to high potential energy. Energy has to be put in to raise that amount of potential energy. And so that would be an endothermic process because we're putting energy into it. Think of it like a spring. If we have a spring stretched out and we let it go, energy is being released, exothermic. Whereas if we have a compressed spring or slinky and we stretch it out, we're putting energy in. That's an endothermic process. And this is true for all bonds. If you break bonds, it's endothermic. If you create bonds, it's exothermic. But the magnitude of that bond breaking or forming is going to be different depending upon the bonds. And so to calculate the actual number for that delta H as opposed to just the sign, we're going to need to use values. And the value we use then is bond enthalpy, which is the amount of energy required to break a bond. And this is going to be exactly equal to the amount of energy that is released when the same bond is formed. So the energy to create a bond is the same as the energy to break that same bond. So if we look at this graphic right here, we see the bond of AA being broken, so that A is now separate from A. The energy needed to break that bond is going to be equal to the energy to form that bond, and we can kind of see that right here. Distance doesn't change if we go up or down. And then we can see that if the bond between A and B is formed, it is releasing energy because it's going down. And so if we wanted to calculate then the overall change in enthalpy for this reaction of AA forming AB, we would start with the bonds broken, and so that's AA. We would figure out the enthalpy for this value, and we would subtract it from the enthalpy of the bonds formed. And this funny looking E right there, that's sigma, that means sum, and so it's the sum of the bonds broken minus the sum of the bonds formed. And that means if you have multiple bonds being broken or multiple bonds being formed, you would add them together before you subtract. So anytime you have a chemical reaction, there's always bonds broken and always bonds formed. That's what a chemical reaction is. But if more energy is released during the formation of products than what's required to break the bonds in the reactants, that is an exothermic process because overall we are releasing energy. As a result, then, the products are at a lower potential energy than the reactants. If we sketch an energy graph like from the last slide, where we're measuring the progress of the reaction versus the energy, we see here that the reactants are at a higher energy than the products, and so that means that change in energy, the difference between these 2 points, is energy that is released. And that would make an exothermic process. Now, if we have an endothermic process, that means more energy is required to break the bonds in the reactants than what's released with the products. And so that means that the products are at a higher potential energy than the reactants. And if we draw our energy graph for that one, that means that our reactants are going to be at a lower potential energy than our products. And so in order to get our reactants from this point to that point, we have to put energy into the system. And so that would make it an endothermic process. So to make these kind of calculations, you would have to look at average bond enthalpies for each individual bond inside of a reaction. So if we wanted to do this for the combustion of methane, we would have to look at all of the different bonds that are taking place in both the reactant side and the product side. So methane, for example, has carbon to hydrogen bonds. But since methane is CH4, that means you have 4 hydrogens bonded to a carbon. And so there's not just one CH bond, there's 4 CH bonds. So that's where the whole sigma thing comes in. It's the sum of. So we have 4 bonds that have 413 kilojoules per mole of energy. So let's go ahead and sum all these together to go ahead and get our overall change in enthalpy. So our equation is going to be the bonds broken summed up minus the bonds formed summed up. Let's do the broken bonds first. So for broken, we have 4 methane bonds, or 4 CH bonds in methane. And so that means we're going to multiply 4 times 413 kilojoules per mole. And we also have our oxygen, that bond that's going to be broken. And so we would add that to the CH bonds. And so oxygen, that's oxygen double bonded oxygen. And there's 2 oxygen molecules. So it would be 2 times 495 kilojoules per mole. And so that value, that would be the sum of our bond energy for the bonds that are broken, would be 2642 kilojoules per mole. Why don't you go ahead and try it with the products, pause the video, and then resume it to check your answer. Alright, so with our products then, carbon dioxide, which is C double bonded to O twice, because we have 2 oxygens on there, so it'll be 2 times 799, and we're adding that to the water, which there's 2 waters, and each one has 2 OH bonds, and so it's going to be 4 times 467. And so the overall bond enthalpy for the bonds formed is going to be 3466 kilojoules per mole. So then in order to calculate the change in enthalpy, we're going to subtract the bonds formed from the bonds broken. And that gives us an overall value then of negative 824 kilojoules per mole. What this means then is this is an exothermic process, so energy is being released, and it's a combustion reaction, so we could have predicted that beforehand. If we were to look at a graph then of the reaction as it proceeds versus energy, we would see that the energy of the reactants is greater than the energy of the products. So that means this change in enthalpy right there, that change in potential energy, is going to be released in the form of heat energy. So here's a differently worded problem. We're going to look again at that water. So if we form H2 and O2 into water, it releases 572 kilojoules of energy. Here's the bond energy for the oxygen to oxygen bond. Here's the bond energy for the oxygen to hydrogen bond. But we don't know what the value of the hydrogen to hydrogen bond is in the H2. So let's see if we can calculate that. So in this case, we know what the change in enthalpy is. It's that value right there. We know the value of the bonds that are formed, and we know one of the bonds that are broken. So then if we apply this equation to the actual reaction, the enthalpy is equal to 2 times the bond energy for the H to H, that's that right there, and then the bond energy of the oxygen, there's only one of those, minus the bonds formed, which would be 4 times the OH bond from the 2 waters that we have. Now, since we have this value, but we don't have that value, we need to rearrange this equation so we can solve for the bond energy of H to H. So then just rearranged, we can go ahead and figure out what the bond energy for H divided by H is by plugging in our values. We know that delta H is going to be 572, and we can find these from the previous slide. Once we plug all of those numbers in, we find out that the bond energy for the H to H bond is 401 kilojoules per mole. So the average bond enthalpy for a hydrogen to hydrogen bond then is 401 kilojoules for every mole of hydrogen gas.